Hello everyone, welcome to the week 5 of this semester. Uh, in this week, I'm going to continue chapter 3, which was about this fourth layer of computer networks, the transport layer. So this week, we are going to talk about connectionless transport layer protocol, which is UDP, and then we talk about principles of reliable data transfer. First, we talk about UDP, User Datagram Protocol, a protocol that does not provide reliability, and the datagrams might be lost, or they might be delivered out of order if you use this protocol. And UDP does not add any reliability service more than what the third layer protocol provides. The third layer protocol, known as IP, provides the best effort service for delivering data, but UDP doesn't add any other reliability service to the third layer, and it is connectionless, which means that there's no handshaking between UDP sender and receiver, despite what we have in TCP. And each UDP segment handled independently of others. It's not like a stream of connected data. Every UDP segment is handled independently, and then it is used for streaming multimedia because it's faster than TCP, and and multimedia streaming is loss tolerant, and if some bits are delivered out of order, it doesn't affect the quality of multimedia that is going to be streamed. And obviously UDP use DNS for translating the host names into IP addresses. And if you want to have a reliable data transfer over UDP, your only choice is to add reliability on the fifth layer, on the upper layer, on the application layer. So you have to have an application specific error recovery if you want to use UDP for non-loss tolerant applications. So here you see some more details about UDP segment. The UDP segment has a header which includes some important information: source port number and destination port number for the purpose of multiplexing and demultiplexing, and then the length of UDP segment including header in bytes, and then checksum. Checksum is used for detecting any error in the process of transferring data. I'll talk about it in the next slides. So this is the UDP header, and then there's an application data or payload that is attached to the header, and then they all make this the UDP segment. And also here you can see the reasons that UDP is popular, because the first reason is there's no connection establishment phase for UDP, because if you add connection establishment phase, it will add some delay to your process. So by having no connection establishment phase, we will save some time using UDP, and also it's simple. There's no connection state at sender and receiver, and also the header size is small. As you see, this is the only information that exists in the header of a UDP, and there's no congestion control, which means that UDP can blast away as fast as desired, despite what we have in TCP, which has a congestion control mechanism. So let's talk a little bit about UDP checksum in the header of UDP segments. we include checksum for this purpose of detecting errors in transmitted segments. What do we mean by errors? We mean if a bit is flipped from 0 to 1 or from 1 to 0, that's called error. So we want to find out whether an error has occurred uh, while transferring a segment or not. That's why we use the checksum. How does it work? The sender of a packet or the sender of a segment treat the content of that segment like a sequence of 16-bit integers. Okay, so that's important. First, the segment can be treated as a sequence of 16-bit integers, and then since we have a sequence of 16-bit integers, we can add them all together using a ones complement sum, which means that the carryout has to be added to um, the summation, and you have to do it again and again for all the elements, for all the 16-bit integers in the sequence, until we reach to the end, to the last integer. And then when sender adds everything together, it puts the summation, the summation value into the UDP checksum field in the UDP segment header. And in the receiving side, when a computer receives the segment, it does the similar thing by adding the sequence of 16-bit integers together and comparing the summation with what we have in the checksum. So if the checksum that it receives is not equal to the summation of all the segment contents, then it means that some error happens, right? But if it's equal, we can say most likely there's no error in transferring information. Why can't we say 100% there's no error? Because we may have some error in a way that the summation of those sequence of 16-bit integers remains the same. It's a very rare situation, but it might happen. So if the checksum is not equal to the summation of those sequence of integers in the receiver side, we can definitely say an error is detected. But if this checksum is equal to the summation of the sequence of integers, we can say with a very high probability no error has detected, no error has occurred while transferring data, but we cannot guarantee 100% that no error has happened. Here is an example of how to add two 16-bit integers. As you see, these two numbers will be added, and the result is this 17-bit integer. We have one carryout bit, and finally the 1-bit carryout will be added with the 16-bit with the other 16 bits of this summation, and the result becomes this sum. As you see, this sum is equal to this 16 bit plus the 17th bit. And when you find the sum in the receiving side, you compare it with the checksum. So now the sum is this, and the checksum that the receiver receives is this one. So when you compare these two, you figure out that they're not equal, which means that some error has happened while transferring data. Next, we talk about principles of reliable data transfer. So the reliable data transfer is very important in a lot of applications, like sending email, or web application, or a file transfer protocol, and many other network applications. So in those applications, what we need to have is a reliable channel between a sending process and a receiving process, right? So this is the ideal model that we need to have a reliable channel that can transfer data between one process and another process. However, the physical layer, the last layer of network, which is wire or wireless, is an unreliable channel, and the data in the physical layer can be altered and can become faulty while being transferred from one party to another. So we have an unreliable channel in the physical layer. However, we want to provide a reliable service for the application layer. So the question is how transport layer can help to provide a reliable data transfer to the application layer while the underlying physical layer is not reliable, is unreliable. To deal with this challenge, we have to have a reliable data transfer protocol in the transport layer, like this one, that in the sending side, in the sending side of the data transfer, we have to have a RDT send. RDT means reliable data transfer send function that the application layer can call, and this function can reliably send data. But this RDT send will call another function which is UDT send, which is the unreliable data transfer. That's the service that the third layer protocol provides the transport layer, and using this UDT send with some magic, we have to construct, or we have to implement this RDT send function so that when the application layer wants to send some information reliably, it can simply call RDT send, and inside RDT send function we have an UDT send function that the underlying uh, layers provide us. On the receiving side, again, we have to have a reliable data transfer protocol on the transport layer that can implement the RDT RCV function, which is reliable data transfer receive function, and this function has to receive data in a 100% reliable manner, which means that the data that receiving side receives is equal to the uh, data that is sent by the sender with a 100% probability. In this slide, you can see all the details about the functions that I was talking about in the previous slide. We have RDT send, reliable data transfer sent, or UDT sent, unreliable data transfer sent, and we have RDT receive, and finally we have deliver data. That's the function that is called by RDT to deliver data to the upper level. So in other words, the receiving process in the application layer use deliver data to get the data with 100% reliability. So in the following slides, we are going to incrementally develop a sender receiver sides of a reliable data transfer protocol, which we call it RDT. But we first create RDT version 1, then version 2, 3, 4, and then while creating this protocol, we consider only unidirectional data transfer. However, when you want to have a bidirectional data transfer, you just need to do the same thing in the opposite direction. So for the sake of simplicity, we only consider unidirectional data transfer, which means one side is sender, the other side is the receiver side. And also we use the FSM diagram, which is finite state machine diagram, to specify the server and receiver side. That's a very powerful tool for representing the protocols on both sender side and receiver side. So in this diagram, we have a bunch of states. So for example, here is state number 1, state number 2. We may have tens of states, and then we can have as low as 1 state. And then between the states, we have arrows that shows state transition. And on this arrows, for example, this arrow is from state number 1 to state number 2. On this arrow, we have two labels. Uh, the top one is the event causing state transition. So the top one shows the event that will cause state transition from state number 1 to state number 2. And the second label, the label in the bottom, shows the actions that has to be taken while we do the state transition. So there might be many arrows going out of one state. For example, in this figure, as you see, we have one arrow from state number 1 to state number 2 and another arrow from state number 1 to other states. And that again shows the event that can make this state transition started and the actions that has to be taken while this state transition is taking place. And also there's a rule for FSM, a finite state machine, and the rule is while you are in one state, the next state has to be uniquely determined by the next event. So if I'm in state 1 and an event happens, I have to be able to find out which arrow should I use for the state transition. For example, here we have two outgoing arrows from state 1. So if an event happens that matches this event, I have to go to state number 2. If an event happens that matches this condition, then I have to take this arrow to use to do the state transition. Okay, so let's focus on the first version of RDT protocol, Reliable Data Transfer Protocol. In this version, for the sake of simplicity, we assume that the underlying channel is reliable. That's not a reasonable assumption, but we assume that the underlying channel is reliable. Therefore, when you call UDT send, this function transfer data with 100% reliability, so there's no need to do further action in the transport layer. So as you see, we have one FSM for the sender side and another FSM for a receiver side. As you see, the FSMs are pretty simple. We have one state for each of these FSMs. In the sender side, the state is wait for a call from above, because we are in the transport layer of the sender side, so we have to wait for the application layer of the sender side to ask us to send something, so it waits for call from above. However, in the receiving side, the state should be wait for call from below, because we are in the receiving side, and the receiving side fourth layer has to receive data from the third layer, from the layer below. That's why it has to wait for call from below. So in the sender side, we have only one state transition, which is from the same state to itself, and this transition will take place if RDT send data is called by the application layer, and the action that needs to be taken upon such event is to create a packet by calling the make packet function with the same data that we receive from the application layer. And after creating the packet, yes, we have to use the underlying channel UDT send to send the packet to the receiver side. In the receiver side, we have to do the exact same opposite things. If the RDT receive packet is called from below, we have to extract the packet and convert it into the data, and then we have to deliver data to the upper level, which is the application layer, using deliver data function. Okay, so now let's focus on the second version of RDT, RDT 2.0. In this version, we assume that the underlying channel may flip bits in packets. So this is a much more reasonable assumption, and we use checksum to detect bit errors. So it's similar to what we do in UDP. However, in RDT 2.0, we have to have the option of recovering from errors. So if some error happens, we have to recover from that error. So the question is, how do we recover from errors if an error happens? To answer this question, let's think about how humans recover from errors during conversation. For example, if I'm talking to you and you didn't hear me, you can simply say, I didn't hear you, please say it again. Or uh, if I say something and you hear it, you can simply use a head movement to show that you are hearing me and you are understanding me. Otherwise, you can explicitly say, I don't hear you, say it again, and I would repeat my point that this is how it works during a conversation between two humans. Now we want to use the similar idea to implement RDT 2.0 so that computers also can recover from error in the similar way that humans recover from errors during conversation. Okay, so to recover from errors, we introduced two different responses from the receiver. Receiver can either say ACK, which is the acknowledgement of receiving the packet with no error, or it can send negative acknowledgement, which basically means the receiver explicitly tells sender that packet had received with error, and the sender retransmit packet when it receives the NAK, which is negative acknowledgement. But if the sender receives the acknowledgement, it means that the packet has gone through without any error. So as you see, RDT 2.0 is smarter than RDT 1.0 because it has an error detection, and the control messages ACK and NAK will be transmitted from receiver to the sender, so that the sender finds out whether the receiver has received the data with error or without error. And if the receiver has received this information with error, the sender has the option of sending the data again. So here is the FSM of both sender side and receiving side of the RDT 2.0. Let's first focus on the FSM of the sender side. In this FSM, we have two different states. The first one, which is the initial state, you see this arrow. This arrow shows the starting state. That's where we start in the sender side. In the sender side, we start by waiting for call from above. That's always true. You have to always wait for calls from above. Above means the application layer of the sending side. And upon the event of RDT send data, upon this event, the sender side of RDT 2.0 has to do the following: has to first make a packet using a data and checksum, and then send that packet over the network to the receiving side. Why do we have checksum here? Because checksum will help us detect any error in the receiving side. So this is what we do when we are in the wait for call from above state in the sender side and we receive RDT send data. Now let's assume that we have done the state transition from this state to the other state. In the second step, we have to wait for ACK or NAK messages, which are the feedback that the sender receives from the receiver side. So in this state, two events may happen. The sender can either receive a NAK or an ACK. This is when the sender receives an ACK. This is the event. So the receiving packet is an ACK. In this event, you have to do no action. This is a sign for no action. If otherwise, it means if the sender receive NAK, that means it has to send it again, right? So it has to call the UDT send again to send the packet and hopes that this time it goes through and the receiver side can receive the packet. So in the first event, when the acknowledgement is received from this receiving side, it has to do nothing, and we have to go back to the initial state and wait for call from above, because we have successfully sent the first packet. So we have to go to the initial state and wait for other requests from the application layer. However, if a negative acknowledgement is received, we have to go back. We have to make a loop and go back to the waiting for ACK or NAK state after sending the packet again. Because again, when you're sending the packet again, you may receive another negative acknowledgement. And if you receive another negative acknowledgement, you have to send it again. And then you may again receive another negative acknowledgement. So this loop may continues forever, but usually it continues until we use this state transition to go back to the initial state and try to send another packet. Now let's look at the receiving side. The receiving side has only one state, and that state is wait for call from below. This state waits for one of these two events. In the first event, you receive the packet, okay, with RDT receive, RDT RCV receive packet, and if that packet is corrupt, that's the first event. If you receive the packet and the packet is not corrupt, then it means that you're in the second state transition. In both state transitions, we have a loop from the initial state to itself. So it's very simple. It's a very simple FSM. But in the first case, when the receive packet is corrupt, you have to send the NAK, which is negative acknowledgement. However, if the packet is not corrupt, you have to simply extract the data from the receiving packet and deliver it to the upper level, which is the application layer of the receiving side, and then after that you simply send the acknowledgement to the sender side, so that the sender finds out that the receiver has received data successfully. Although RDT 2.0 seems to solve the problem, it has a fatal flaw. What's the problem with RDT 2.0? The problem raises when an ACK or NAK message that the receiver sends to sender as a feedback becomes corrupted. So if the receiver sends ACK message to the sender and the sender checks the checksum of that message and see that it is received with error, then the sender cannot trust that feedback. It has to send that packet again because the receiver side might have sent any feedback, because the feedback that is received by the sender was with error, and sender doesn't know whether that feedback was an ACK or NAK. So if the sender decides to send it anyway and retransmit the data anyway, no matter if it is ACK or NAK, you may have a possible duplicate, because if the receiver acknowledges the first packet, the first data segment, and then the sender wants to send it again, receiver receives one single segment twice. So that's not a good idea. However, that would be the only choice, and we have to deal with duplicates in the receiving side. So in the next step of improving the RDT protocol, we decide to ask sender to retransmit the current packet if the ACK or NAK feedback from the receiver is corrupted. And in order to handle duplicates, the sender adds a sequence number to each packet. Okay, so I'll talk about the sequence number in the next slide. And this sequence number can handle the duplicates. So the receiver discards and doesn't deliver up the duplicate packet if it has the same sequence number. So this would be a solution for handling duplicates. I'll talk about it in the next slide in detail. And then, this rule of RDT 2.0, which sends one packet and waits for response, is called stop and wait. So here is how we improve the RDT 2.0 to get the RDT 2.1. In this version, the sender handles faulty acknowledgement and negative acknowledgements from the receiver. And as I said, to handle it, it sends the packet again, but in order to avoid duplicate packets, it adds a sequence number. The sequence number is either 0 or 1. So here is the sender side. In the sender side, we have a more complicated FSM with 4 different states. In the first state, the initial state, it waits for call 0 from above. 0 is the sequence number of the first packet, and when it gets the request from the upper level to from the upper layer to send the packet to send some data, it first make a packet and call it send packet. To make the packet, it has to use the data, it has to use the checksum, and then it has to use the sequence number, which I said at the beginning, it's 0. And then after making this packet, it sends it through the network, and we have a state transition to the second state, in which the sender waits for the acknowledgement or negative acknowledgement from the receiving side. So in this state, two events may happen. In the first event, the sender may receive a packet from the receiving side, and that packet is either corrupt or it's a negative acknowledgement. In both cases, it sends the packet again. However, if it receives the packet and the packet is not corrupt and the packet is an acknowledgement from the receiver side, it simply does nothing and it goes to the next state, which is wait for call 1 from above. So in this state transition, we simply go to the state that is symmetric to the initial state. In the initial state, we were waiting for packet from the above, and that packet would have sequence number 0. In this state, we set the sequence number equal to 1, and we only have two sequence numbers, 0 here, 1 here. And that sequence number can help us, can help the receiving side handle duplicates. Okay, so let's talk about this state, the third state, which waits for call 1 from above. If the event RDT send data happens and the upper layer asks for sending some data, again it sends the packet by making the packet it sends the packet by first making it. To make the packet, you have to use the data, the checksum, and then the sequence number, which is 1 this time. It was 0 here, it is 1 now. And then after making the packet, it has to send it again through the UDT, unreliable data transfer channel, to the, and then we have a state transition to the last state, which is wait for acknowledgement or negative acknowledgement of the packet with sequence number 1. In this, this is another state which is the symmetric to what we had here. This wait for ACK or NAK 0 waits for acknowledgement of a packet with the sequence number equal to 0. Here we have the same scenario, but for a packet with the sequence number 1. So in this state, we may have two different cases. In the first case, we may receive a packet from the receiving side, and that packet is either corrupt or contains a negative acknowledgement from the receiving side. In this case, we have to send the packet again and wait again for the acknowledgement or negative acknowledgement of packet with sequence number 1. However, if we receive the packet and the packet is not corrupt and it's an acknowledgement from the receiving side, then we can make sure that the packet with sequence number 1 has received in the receiving side successfully, and there's no need for further action. We can simply use a state transition to the initial state and wait for call from 0 wait for call 0 from above again in the initial state. So that's the whole idea of a sending side. As you see, we showed this sender side with the FSM with 4 different states. These two states are symmetric to these two states. This is a symmetric to this one, and this is symmetric to this one. They're basically the same as, these two are basically the same, but this one is with sequence number 0, this one is with sequence number 1. Same for these two. Now let's look at the receiver side of RDT 2.1. In this FSM, we have only two states. In the first one, it waits for 0 from below, sorry. In this one, we have wait for 1 from below. Wait for 1, which means wait for packet with sequence number 1 from below. Here is wait for packet with sequence number 0 from below. So the initial state is wait for 0 from below, and there are three different possibilities. There are three different events that may happen in this state. The first event is when you receive the packet and the packet is corrupt. Obviously, you have to send the negative acknowledgement to the sender. That's an obvious scenario. The other scenario is when you receive the packet and the packet is not corrupt and has a sequence 0. So the sequence number is the same as what you expect. We expect 0, we got the sequence 0, therefore that means it's a packet that has arrived for the first time. It's not a duplicate packet, so simply extract the packet, and it extracts the data and it delivers data to the upper layer, and then sends an acknowledgement to the sender, and it simply we have a state transition, in this case from the first state to the second state. However, there is one more case in which we can make sure that we would be sure that we have a duplicate packet. Here is the third case which shows duplication of packet that is received. So the packet has been received before. That means we have a duplicate packet, and it has to simply drop the packet because the receiver side is not interested to receive duplicate packets. So let's see how this transition looks like. The event that we make sure we will figure out that the packet is a duplicate packet is when you receive the packet is not corrupt, and has a sequence number of 1. So we were waiting for sequence number 0, and what we get is a sequence number 1. So that's a suspicious event. Why? Because you are waiting for a packet with sequence number 0, but you receive a packet with sequence number 1. What does it mean? It means that this packet has been sent twice by the sender. Once when we were in the wait for 1 from below state, and now the second time when we are waiting for 0 from below. So the sender side has sent the packet twice to make sure that it is received. Why it happens? Because the receiver has sent an acknowledgement to the sender side, but the sender side received that acknowledgement in a faulty manner. It didn't receive that uncorrupted. The acknowledgement that it receives by the receiver was corrupted, and then the sender has decided to send it again, but receiver has received the packet completely fine without any error, and it has received the ACK, but the ACK was faulty. So this is the event that you can make sure that we have a duplicate information, a duplicate packet in the receiving side, and what we need to do is simply make a ACK packet again and send it again to the sender side, but we don't need to really extract data and deliver it to the upper level, because we have already done it in the previous step. It's a duplicate data. You can simply drop it. You don't need to extract data and deliver it to the upper layer like what we did here. And then the second state is exactly same as the first state, but in a symmetric manner. This time we have we are waiting for a packet with the sequence number 1. Here we were waiting for a packet with sequence number 0. In this case, if the sequence number is 1, we extract data and deliver it to the upper level. However, if the sequence is 0, you don't need to deliver it to the upper level. This is again the sign of duplicate data. All you need to do is send another acknowledgement to the sender and hope that this time the sender will receive the acknowledgement without error, and the sender doesn't send the duplicate data again and again. So let's look at the questions regarding RDT 2.1. The most important question is in the sender side, and the question is why two sequence numbers 0 and 1 are enough, and why. I don't want to give you the answer right now. I just want you to think, but think about this. If we had three sequence numbers, 0, 1, and 2, that the reliability would be closer to 100% than what the reliability is now. So the reliability here can be very, very close to 1, but it is not 1. If you add one more sequence number, the reliability would be much closer to 1. What would be much closer to 100%. So I want you to think about it and think why two sequence numbers are enough. I'm going to use this question for one of the assignments, and you will eventually see the solution, but I don't want you to see the answer now because I want you to think about it, and after you think about it, I'll give you the correct solution. So RDT 2.1 was a little bit too complicated. So in RDT 2.2, we simply remove the negative acknowledgement from the protocol. It's a NAK free protocol and it has the same functionality. The only difference is it doesn't use NAK, and as you see here, it doesn't change anything, and the performance remains the same. How? The idea is, instead of sending the negative acknowledgement to the sender, you can simply acknowledge the previously received packet. So when the sender receives a duplicate acknowledgement, it results in the same action as a NAK, as a negative acknowledgement, which is retransmitting the current packet. And this is how simple you can remove negative acknowledgement messages from your protocol. So RDT 2.2 doesn't have any negative acknowledgements. It only works with acknowledgement messages. Here you can see how both the sender side and receiving side of RDT 2.2 has changed compared to what we had in RDT 2.1. The red the parts are the ones that we have changed them compared to what we had in the RDT 2.1. So instead of sending a negative acknowledgement, we send the acknowledgement with sequence number 1. And also in the sender side, as you see, instead of saying that we receive a negative acknowledgement, we say if we receive an acknowledgement and the sequence number is 1 and we were waiting for 0, that means that we are receiving duplicate acknowledgements. All you need to do is to send the packet again. So far we only covered the channels which could alter or flip the data bits. However, in the third version of RDT protocol, RDT 3.0, we consider the case in which the underlying channel can lose a packet. We may have data loss, as we see in the previous chapters. So what happens if we have a we have an underlying channel that can lose packets, okay, either data packets or control packets, which is acknowledgement packets. So in this scenario, when you lose a packet, the checksums doesn't work anymore because you don't receive a packet to check the checksum, right? So here is the approach that we use for RDT 3.0. The sender waits a reasonable amount of time for the acknowledgement the message from the receiving side. If no acknowledgement received in a certain period of time, then it means that either the data packet has been lost at the middle of the way or the acknowledgement has been lost. So in both cases, it has to retransmit data for the sake of reliability. But the question might be, what happens if we uh, send duplicate data? That duplication has been taken care of before in the RDT 2.2 by adding a sequence number. So there's nothing challenging anymore, and all we need to do is we need to have a countdown timer so that the sender side can wait a reasonable and finite amount of time before retransmitting data. And obviously the receiver has to specify the sequence number for the packet that is being acknowledged. So here is the FSM of the sender side of RDT 3.0. As you see, the first state didn't change really. When you get a send data request from the upper layer, you simply add data and checksum and 0, which is the sequence number of the first packet, to make a new packet, and then you send the new packet to send that packet to the through the UDT, through the unreliable data transfer channel. However, the only difference here is we start a timer. Why do we start a timer? Because we have to count down the amount of time that it takes for the receiver to respond. So this timer is around the RDT, around it's almost a bit more than RTT, which is round trip time. So we have to give enough time for the packet to be sent to the receiving side and be transferred back, and then the feedback is transferred back to the sender. So you have to wait for more than the round trip time before we stop the timer and retransmit data. So that was the sender side. That was the initial state of the sender side. Now let's talk about the second state. In the second state, when we have in the second state, we have three different scenarios. One scenario was to receive a packet that is corrupt, or it is acknowledging the wrong sequence number. So we are waiting for acknowledge 0, but we get acknowledge 1. So in any of these two cases, either this packet is corrupt or the acknowledgement is received for a different sequence number, we really don't have to do anything, because we have to wait for the timer to be timed out. And if we reach to the timeout of the timer and still we didn't receive any good news from the receiving side, then we have to send the packet again. Before timeout, we should not do anything. So the second event is when you have a timeout. In the case of timeout, you have to simply send data again and restart the timer. Okay, Why should we restart the timer? Because this time again we might have the same scenario and the packet might be lost at the middle of the way, or the packet might be delivered but the acknowledgement might be lost at the middle of the way. There is one more case where there is one more possibility when we are in the second state, and that's when you receive a packet. A packet is not corrupt, and it's an acknowledgement of the right sequence number, which is 0. In this case, you can simply make sure that the packet has been received by the receiver successfully, and you simply stop the timer and wait for uh, the application layer in this state, but this time you wait for a packet with the sequence number 1 this time. And we do the same things in a symmetrical manner for the third and fourth step. These two steps are symmetric and these two are symmetric. The only difference between these two is that this one has a sequence number 1, this one has sequence number 0, but the rest are all the same. So here you can see a scenario in which the packet is lost at the middle of the way, and RDT 3.0 can handle the situation. Look at this diagram. First, the sender sends the packet with the sequence number 0. So packet 0 is sent from server to the receiver, and the receiver successfully receives the packet. And then since it receives successfully, it issues an acknowledgement 0 to the sender side, and then the sender side receives the 0 acknowledgement without any error, and then it sends the next packet. So it sends packet with sequence number 1, but this packet will be lost at the middle of the way while it's being sent to the receiver. So the receiver hasn't received anything by the sender, therefore it doesn't need to respond to uh, any receiving packets, because receiver here doesn't receive anything. So when the sender sends this packet, it waits for either a timeout or a correct acknowledgement. If it Since the packet is lost at the middle of the way, we would have a timeout after some point because the receiver will not react to anything. And after the timeout reaches, then the sender simply resends the packet with sequence 1, and this time it will be received by the receiver, and then the acknowledgement is sent back to the sender, and then again we have to go back to the sequence number 0 and send the packet with sequence number 0 from the sender to the receiver, and the receiver send the acknowledgement back to the sender, and this will happen again and again. And that's how RDC 3.0 handle data loss in a connection by using a simple timer, and in the event of timeout, it has to resend the packet. So it's a simple, straightforward scenario, and it's a simple, straightforward protocol. In this part, in part C, you see another scenario in which this time the acknowledgement the acknowledgement of receiver has been lost at the middle of the way. It doesn't make that much of difference. Again, the sender waits for either a timeout or a correct acknowledgement. Since it doesn't get the acknowledgement and the acknowledgement is lost here, so it reaches a timeout, and the timeout causes the sender to resend the packet again. But if you look at the scenario number, this scenario, you see that timeout is not always caused by packet loss. Sometimes there may be a very long delay because of data congestion in the network, and for example, the acknowledgement is received by the sender in a very long time. It is received by sender longer than the time that the timeout allows, and then uh, in this scenario, since sender receives the acknowledgement of the receiver very late, it resends the packet again, but when the receiving side receives the packet, it figures out that the packet is a duplicate packet, and it simply ignores and drops the packet and sends another acknowledgement to the server side, to the sender side. Although RDT 3.0 is correct and it's very reliable, but the performance is terrible. Let's assume that you have a 1 gigabit per second link and the propagation delay is 15 milliseconds, and then we have a packet size of 8,000 bit. So the delay of transmission is equal to L, which is the size of the packet, divided by R, which is the transmission rate. If you do this division, you get 8 microseconds as a delay of the transmission delay. However, the utilization of sender, which is the fraction of time that sender is busy sending information, is equal to the same transmission delay divided by the transmission delay plus RTT, round trip time, which is much larger. It's like the 30 milliseconds is the RTT. However, the transmission delay is 8 microseconds, which is much smaller than 30 milliseconds. So if you divide these two numbers, divide L by R, divide by RTT plus L by R, what you get is this very small utilization. So how did we get this 30 millisecond? Because the propagation delay is at 15 milliseconds, so the round trip time would be 2 times the propagation delay at least, plus some other delays which we ignore. So it's at least 30 milliseconds. However, for 1 kilobyte packet, you only need to have 8 microseconds transmission delay. So every 30 milliseconds, we send only 1 kilobyte of data, and that would come up with a throughput of 33 kilobyte per second over a 1 gigabit per second link. So that's ridiculous, because you have a very high speed link, but you cannot send information with the speed of more than 33 kilobyte per second. Why? Because you want to have reliability. So the network protocol limits the use of physical resource. We have to think about a smarter reliable data transfer protocol that doesn't suppress the performance this much. So here is the calculations that we need to show that stop and wait operation of RDT 3.0 will make the utilization of sender very, very low. As you see, the utilization is even less than 1 over 1,000. So an alternative to what we saw in RDT 3.0 is to use pipeline protocols. The pipeline protocols, pipelining is a very interesting idea. Instead of sending one packet at a time, we send multiple packets, and the packets that are flying over the network have not yet been acknowledged. So when you are sending 10 packets, none of those 10 packets are acknowledged, but they will be gradually acknowledged as the sender sends more data. This is how we can increase the utilization of the sender. And to make this pipeline protocols possible, we need to have much more sequence numbers. So we have to expand the range of sequence numbers, and we should have to be able to buffer data at the sender and receiver. Two of the generic forms of pipeline protocols are called go back in and selective repeat. We'll talk about them in the future slides. So here is a quick calculation which shows that if you are using pipelining and send 3 packets at a time, what you see is the numerator here becomes 3 times larger, 3L divided by R, while the denominator, which is the time that it takes for these 3 packets to be sent, would be the same as what we had before, which is 1 RTT plus L divided by R. And as you see, the utilization will be increased by a factor of 3. As you increase the number of packets linearly, the utilization will also increase linearly. So let's take a look at these two protocols, go back in and selective repeat, which are two pipeline protocols for reliable data transfer. In go back in protocol, the sender can have up to n unacknowledged packet in the pipeline. So instead of sending one at a time and stop and wait, we send n packets before waiting for any acknowledgements. The receiver only sends cumulative acknowledgements. It doesn't send acknowledgement for each packet. It sends acknowledgement when it receives like a bunch of packets, and it says, okay, I received these sequence numbers. Okay, and it doesn't acknowledge a packet if there's a gap between if there's a gap. For example, if packets 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are received, number 11 is not received, but number 12, 13, 14, 15, 16 are received, it only sends acknowledgement for the first 10. Because number 11 was not received, and that's a gap, so it doesn't acknowledge cumulatively after 10, after 11, because 11 was not received, and there's a gap here. So the sender has a timer for all this unacknowledged packet. So the oldest unacknowledged packet has a timer, and when that timer expires, the sender retransmits all the unacknowledged packets in the pipeline again. So it looks a little bit scary, because at the time that the timer of the oldest unacknowledged packet expires, we may have many unacknowledged packets, so you have to retransmit them all. Obviously, the performance would be affected by this event negatively. How about selective repeat? Selective repeat is a bit smarter, but it's a bit more complicated. Let's see how selective repeat is different from go back in. In the selective repeat, the sender can have up to n unacknowledged packets in the pipeline. So it's the same as what you have in go back in. However, in the selective repeat, the receiver sends individual acknowledgements for each packet. It doesn't send cumulative acknowledgements. So it's a bit more complicated receiving side. It has a more complicated receiving side than what we had in go back in protocol. And then one more difference is the sender maintains timer for each unacknowledged packet separately, and when the timer expires for an unacknowledged packet, the sender retransmits only that unacknowledged packet. It doesn't transmit all the unacknowledged packets, because every unacknowledged packet has its own timer. But in go back in, if you remember, we had one timer for the oldest unacknowledged packet. So let's take a closer look at go back in protocol, the sender side of this protocol. As you see, in this figure, we have four different packet types. The green ones are the ones that the sender has already received the acknowledgement from the receiver, uh, and then we have the yellow ones, the ones that the sender has already sent through the pipeline but has not yet received the acknowledgement from the receiving side. And then we have some blue packets that the sender is in the process of sending them. And then we have some whites which are not even in the window size of not in the window of size n of the sender. So the sender has a window with size n, which starts from the first packet that has not yet acknowledged, and it continues for n consecutive packets, and all of the packets in this window are considered to be candidates for sending through the pipeline. They will be sent through the pipeline one by one, and anytime that we receive a cumulative acknowledgement, we have to shift this window forward, uh, because the window only contains the packets that have not yet acknowledged or are about to be sent, and obviously the receiver has not yet acknowledged the packets. So let's consider the scenario when we have a cumulative acknowledgement. When we have a cumulative acknowledgement, we receive a acknowledgement message like this: ACK with a number which is a sequence number of the last packet that is acknowledged by the receiver. So when we receive this from the receiver, that means the receiver acknowledges all the packets up to and including to the sequence number n. So all the sequence numbers equal to n or less than n has been received by the receiver when we receive this ACK n from the in the sender side. Obviously, the sender may receive duplicate acknowledgements, and that's fine. It can simply ignore the duplicate acknowledgements. Also, as I said before, the timer is for the oldest in-flight packet. So this would be the oldest in-flight packet, this yellow one. That's a timer. So the timer is kept for the oldest in-flight packet, and also when we receive a timeout n, that means that we have to retransmit packet number n and all other packets with higher sequence in the window that we have for the sender side. Here you can check out the details of the sending side of go back N protocol. It is a pretty straightforward diagram. We have only one state, one FSM, the waiting state, and there are four different transitions from the state to itself, obviously because we have only one state. As you see, in the case of timeout, we have to start the timer again and send all the packets starting from base to next sequence number -1 to the receiver again. So this is a retransmit of all the packets that have not yet acknowledged by the receiver side, by the receiving side. So base is in this case, base is the first unacknowledged packet, and next sequence number -1 is the end of the last one in the window. So it's the last packet in the window of the sender side. So you can check other cases. For example, if you receive a RDT send data, you simply check whether the next sequence number is less than base plus n or not. N is the size of the window. If this is not the case, it simply says I refuse sending data because it cannot send more than n packets at a time. The sender has to, I mean, the protocol has to send up to n packets at a time without getting acknowledgements. And but if the next sequence number that it receives from the upper layer, from the application layer, is less than base plus n, which means that if it is inside the window, it can send the data. So what it does is it makes a packet for the next sequence of data, and for this next sequence number and the data, and then it simply sends that packet through the unreliable data transfer using this function. And then if base is equal to next sequence number, then it simply starts a timer. So it starts a timer if the sequence, if it is the next sequence is the base, which means if it's the oldest unacknowledged packet. And then it simply increment the next sequence number, because you have to increment it for the next RDT send function that will be called by the application layer. And there are one more cases here. There is one more cases here, but there is one more case here. If the packet is received and it is not corrupt, then base should be equal to get acknowledgement number received packet plus 1. So base should be set to the acknowledgement of to the sequence number of the last acknowledged packet. And if the base is equal to next sequence number, you have to simply stop the timer. Why? Because all the packets have been received, and then otherwise you have to start the timer again for the other unacknowledged sequences, for the other unacknowledged packets. And also in the receiving side of GBN, we have an expected sequence number, the number that the receiver expects to receive, and it simply use that sequence number to make acknowledgement packets and send it back to the sender side when it receives a not corrupt packet from the receiving side. Here you see the GBN in action, and you see how the windows will move forward from 0, 1, 2, 3 packets to 1, 2, 3, 4 packets and 2, 3, 4, 5 packets after receiving the acknowledgement 0 and acknowledgement 1. And here you can see what happens if, for example, the second packet causes a timeout. It has to, as you see, the sender side has to send the second packet again, not only the second packet but packet number 3, 4 and 5, since all of these packets are in the window of the sending side. And then in the selective repeat protocol, we have a more complicated scenario. Every packet has to be acknowledged, individually. The receiver has the responsibility of acknowledging every received packet individually, and we have to buffer packets if we want to receive them in order. Uh, and then the server only resends packets which are not received. It doesn't send uh, all the packets with the sequence number greater than a number, like what we saw in the GBN protocol. And the sender has a timer for each of the unacked packets, not for the oldest unacked packet. For every unacked packet, we have a timer. So as you see, it's a much more complicated and harder to implement protocol than what we saw in GBN. And the sender window has n consecutive sequence numbers, and it limits the sequence number of uh, send and unact packets by only focusing on the window of n packets. So here we show how selective repeat sender and receiving side view the packets and how they define their windows. In the sender side, the window has size n the same size as the window of the receiving side. However, in the sending side, we have three different packets in the sending in the window. One is yellow one, which is the ones that are have been sent but not yet acknowledged. Then we have green one, which are already sent and acknowledged, and then we have blue ones, which are not yet sent, but they are going to be sent. So as you see, the yellow ones can be between the green ones, and the green ones can be between the yellow ones. So it's not like what we saw in the GBN protocol, because in GBN we would retransmit all the data if all the data after a sequence number, if a sequence number uh, was failed to be transmitted to the receiving side without error. But here in the selective repeat, it's not the case. Therefore, we may have some green ones between yellow ones and some yellow ones between green ones. And for such sender side, we have another schematic view of packets in the receiving side. In this schematic view, as you see, we have the window side with the window of receiver a few blocks further than what we saw for the sender side. So in this window that receiver stores, we have some out of order but already acknowledged packets. For example, these pink ones have already been received by the receiver, but they have been received in an incorrect order. It means that there are some other packets with lower sequence numbers that have not yet received by the receiver, uh, and there are some dark gray packets that are expected to be received by the receiving side, but they have not yet received. And we have a bunch of blue ones. These blue ones are the ones that if they will be received by the receiver will not throw them out. The receiver just keep them, but by buffering them as out of buffer packets, because these two gray packets have not yet received by the receivers, so we have to keep them in order. Therefore, you have to buffer them, and then you have to buffer the pink ones, and then as soon as you get these gray ones, then you can shift your window forward and wait for even further packets. Here you can see the pseudocode that both sender and receiver follow in the selective repeat protocol. It is the same as what we saw before, so I'm going to skip this. You can take a look at it yourself. Here you see the selective repeat in action. Uh, for example, if you want to compare it with the GBN, when packet 2 here is lost at the middle of the way, and the timer for packet 2 reaches here, only the sender retransmit packet number 2. It doesn't retransmit all other packets after 2, which is 3, 4, and 5. So that's a big difference between GBN and selective repeat. GBN is less efficient, but selective repeat is much more complicated. Much more complicated, and it needs more equipments and more infrastructure. Also, in a selective repeat protocol, we have to have a relation between the window size and the sequence number. Otherwise, it will reach a big problem. I want you to take a look at this slide, and also the similar part in the book, and figure out what relation we should have between the sequence numbers and the sequence number size and the window size, to avoid the problem that is explained in this slide and also in the book. I'm going to include this one in in the homeworks too, in the assignment too, and then I will post the solution after the deadline, but I want you to think about it. That's a very interesting challenge for your mind.